Um,
Good evening, sir.
Good evening. Just wait for some time.
Sir, don't.
Yeah.
Sir, sir, force and charges and direction, negative gradient.
Repeat again.
Sir, force and charges in direction of P and the question
Force and charge.
is in the direction of E for positive sir, negative gradient, sir. Negative gradient.
Yeah. Uh,
Sir,
Force
what
on
is
a
answer?
charge. When the potential gradient is known. Potential gradient is known. Right. So, for example, the for example, we take this point charge. Okay. So the potential surface will look like this. They will be nearby as you go away. Will become farther and farther away. Okay. So suppose, for example, say there's this 10 volts, and next is 8 volts, and the next will be 6 volts, which will be 4 volts. So you have to draw equivalent with equal intervals of the voltage. So there won't be any equivalences of 5 volts and all because I'm drawing equivalent at the interval of 2 volts. So from here at this point, the gradient of potential is electric field is minus dV by dr. So at this point, by this much distance, I'm getting a drop of 2. But the same drop of 2 volts, I'm getting over a larger distance. So here the electric field at this point, say V2, and the electric field at this point V1. So since PR is small for this first part, so V1 will be greater than V2. So we'll take the third part. This one again, the voltage drop is 2 volts, but the DR is small. So V3 will be less than V2 according to this. Is that clear?
Yes, sir.
Okay. So the place is where the electric field is stronger. The equipotential surface. And say another point equipotential is like this. So here I can say the potential at this, sorry, the electric field at this point E2. And if I have to compare the electric field at point E1, so E will be greater than E2. Because the gradient of the potential at this point, d by dr is greater compared to the gradient of the potential at this point. Another way of representing the electric field is more at the particular point is the rings of the electric field lines. So at this point, the field lines will be closely packed. Here the field lines will be far away. Okay, so this is another indication of how the electric field can be represented. Another one is a basic one. The electric field is strong here. That will be length of the electric field vector will be more here. So the length of the electric field vector will be short. So three ways I can convey the magnitude of the electric field. One is with the length of the electric field vector. Now the electric field lines will be dense or closely packed when the electric field is strong. Like here compared to this one. Another thing is by equipotential surface. The equipotential surface will be closely arranged. If the electric field is small and the electric field is weak, means the equipotential will be far away. Another thing is the angle between the electric field and the equipotential surface will be 90 degrees. Field lines are curves. Field lines are curves. But equipotential surface are surfaces. For example, for a point charge, the field line is a straight line which goes like this in all directions equally because of symmetry. There's a straight line, and the equipotential surface are spherical shells. That is, the sun should be 90 degrees. Okay, so electric will be perpendicular to the equipotential surface. Is that clear? Surya Prakash. You asked the doubt, no?
Yeah.
Okay. Is it clear? Akshay? You have to unmute.
Sir,
Yeah.
yes, sir.
Okay.
Yes, sir.
Yeah. So this is the rest of concepts you should know. So any other doubt? So the latest one I added is this one, electric field along the axis of a dipole. You have to derive, okay, and the approximate that we use is the dipole is small in the sense that the size of the dipole is small compared to distance at which I'm finding the electric field or potential. So this is a dipole minus q and this q. Okay, so I'm finding electric field at a say along the axis at a point which is a distance r from the center of the dipole, and the size of the dipole is 2a. So we can find the expression of this electric field this point under the assumption that or at a distance where r is much greater compared to 2a, or the same as I saying r is much greater than a, because this approximation is used by deriving the expression for the electric field. So this approximation is used. So you should know this derivation. So electric field on the define electric field on the axis. So that's by superposition principle. So you have minus q and plus q separated by distance to a. So you're finding electric field at this point at left. Okay, so the charge q is a distance of r minus a, and the distance of minus q is r plus a. So that's why the electric field is given like this. This is the definition of electric field, q by distance square. And here this is the exact expression. But if you make this approximation, okay, which is valid for points r which are far away compared to the size of the dipole. There I can neglect this E square in the denominator. So it will become like this. And then Q and QA I can combine as P. Okay. So finding the potential electric field on the axis of the dipole. This one I added and then parallel with capacitor with two dielectrics. So here parallel capacitor like this, and there are two dielectrics here, K1 and K2. So this is one plate. So this can be positive and this can be negative plate. So between these two, there are two capacitors in parallel. So this is equivalent to this part is C1, this part is C2. So C1 parallel is C2, and C1 is A1, epsilon naught, A will be A by 2. So it's half the area. The plate will be like this. So this K will be the half the area, and the K will be the another half. Okay, but the distance between the plates is same for both. It will be D for this one and D for the first one also. So A divided by T. And this in parallel capacitance will add. It is K2 into epsilon of A by T by T. It will be the equivalent capacitance of this capacitor. So this will be around that. Now the another thing I added is this one, radius of circular path. So you have charge moving in a uniform magnetic field, which is there in the book. Okay. This one, the magnetic field is uniform because the cross is equally spaced everywhere, and the velocity, initial velocity is perpendicular to this magnetic field. So because there will be a force QV cross B, this force. Okay, so the direction of force you can figure out. QV is towards B is towards right, and B is into the plane of paper. So I get the force direction as inwards. That will be towards the center. So it will make a circular path in anti-clockwise direction. So the forces acting on this charge are QV cross B. That is the only force which will create an acceleration towards the center, which is mass into centrifugal acceleration, which is mv square by r. So these two forces will be in balance. QV cross B, which is same as Q into B into B, because angle between B and B is 90 degrees, because B is perpendicular to this plane. So angle between B and B is 90. So it becomes just QEB. That's equal to centrifugal force. So how much you get the radius of the circular path as this one. So this you should know. Charge in uniform B. We know the circle is will be perpendicular to B, and we have to get the radius of the circular path. Okay, this is the new thing I added. So this thing I want to explain about cells in series and parallel. So you have a two cells in series, E1, E2. There is some internal resistance because a real cell, R1 and R2. So if we replace by a single cell of E equivalent, then it's equal to be E1 plus E2, and there will be internal resistance which is R equivalent, which will be equal to R1 plus R2. This simple series combination, voltage is add and resistance will add. But the thing is, this voltage of V is for ideal cell. Well, across the terminals of the cell, the voltage will be V. Okay, and since the positive terminals of the cell is this way, this will drive a current in this direction. So this is the direction of the current. Same V will be here. V. This is plus and that is minus. And the same current will flow. So this V I can write as V is dropped from left to right, from positive to negative terminal. So this V drop is, you have to sum the drops. So there's a drop here of value equivalent. And against the direction of current, in a resistor, there will be a voltage rise. Because the property of resistor is along the resistor, the current is flowing in this direction, then these are higher potential, these are lower potential. Okay, so along the direction of current, there will be a voltage drop. Along the direction of current in the resistor, there will be a voltage drop. So here we are going against the direction of current, we're moving left to right. So there is a voltage rise. Okay, so this is the voltage rise. I'll put a minus sign, and the voltage rise is having to R equivalent. So here now the relation between the terminal voltage and the current is a straight line. Once V1 and R1, V2 and R2 are fixed, E equivalent is fixed, and the R equivalent is fixed. So the only variables are V and R. Okay, so now if we draw this plot of V versus I, so if you put I equal to 0, I get the value of V as V equal. So this point will be V equivalent. Okay, and this is a straight line because this will become Y equal to mx plus c, where the slope is minus R equivalent. So it will be a negative slope graph. So the V versus I graph will look like this. So if this V equivalent is given, say for example, from the graph, if I read this 10 volts, and they say this equivalent is made up of Y identical cells. That means that E equivalent is 10 volts, and E equivalent is nothing but E1 plus E2 plus E2 epsilon of E5. But since they are identical cells, it will be 5 times the individual cell EMF. So from there, I get a cell of EMF of individual single cell as 2 volts. Okay. So is this idea clear? So combination of cells has got equivalent and R equivalent, and they say this is a series combination, and they are given the graph of V versus I of this combination. So looking at the equation of this equivalent, this one, so I can figure out that the y-intercept which I get from putting I equals will be E equivalent. So this value is E equivalent. So I can read that value from the graph, and E equivalent is series combination of cells. So there are 5 cells means 5 times E. So from the regular, name of a single cell as 2 volts. That's why I written here. Series parallel. Okay. So for V versus I is given. From there I can find E equivalent. And I can from there I can find out E of individual if the cells are identical. So just go through the list of concepts I given. Which one I have to discuss now?
Sir,
Ah,
sir, advantage or disadvantage of low spring constant, sir.
what?
Advantage or disadvantage of low spring constant.
Yeah. Uh, it's a very simple concept. So let me discuss with the linear spring. Okay, it is fixed at one end, say attached to a wall or something, and here I'm applying a force. Okay, let the spring constant be K, and this force is F, right? So the applied force, say it's producing compression of X, so F equal to K into X. Suppose it's a tight spring, then the value of K is large. Okay, so the K is large. In that case, when I apply, say, given force, then the X will be small, right? Okay. But if the force itself is small force, then this X will be still small, more small, right? Or I should say smaller. Okay. So here, this sort of a spring, which is like a large value of T, it's not appropriate for measuring small forces. Okay. But if the spring constant is small, if K is, or I should say less, then for us, given small force, then the spring will compress appreciably. So I can measure small force using a spring which has got less value of K. Is it clear? See, the amount of compression in the spring is proportional to the force, right? And also the compression is will be less if K is more for a given force. Okay, so if the force is small, if the spring has got small K, then X will be appreciable. Is it clear or not?
Yes, sir.
So equal to K into X. Okay, the sign. Okay, let me assume K is 1000 into X. Okay, for this thing, if I apply a force of 1 Newton, okay, then it means X is 10 raised to minus 3 meter. Okay, so but suppose I have a second spring where F is say 10x, where K is 10. For the same 1 Newton, okay, X will be 1 by 10 meter. So that is 0.1 meter. Okay, so this is a very small value, but this values I can measure. So for the force of 1 Newton, I have to check it's better to choose a spring constant which has got value of 10 compared to 1000. Okay, similarly for a spiral spring, this linear spring where I applying a linear force. Similarly for a spiral spring, it will be like this. So I'll be applying a torque either this way or that way. Okay. So when I apply the torque, we will get wound. So the applied torque is proportional to the amount of winding K into theta. Okay. So if the torque is small, say 10, so K should be small for theta to be appreciable value. If K is large means theta will be very small, which is not easy to measure. Okay, so the advantage of having small K is we can measure small current, because small current will produce small torque and they will produce a deflection, appreciable deflection if K is small. Okay, but with this spring which has got small K, if we try to measure large current, okay, then the spring will get fully wound. Okay, so this full winding happens at a current of say 5 amps. Okay, so it will reach the full scale deflection with the scale. So we'll go to the full scale deflection. After if we make 6 amps also, will still be the same level, or it will break also. So the advantage of having small keys, you can measure small currents, but the disadvantage is you cannot measure large currents. In some sense, if the spring constant is low means it's sensitive, so it can measure small currents, but it's not useful for measuring large currents because the spring will get fully wound and it may damage the instrument also. Okay.
Okay, sir.
So anything else you want me to discuss?
Sir, mutual inductance, sir.
Which one?
Mutual inductance.
Mutual inductance, yeah. Simple concept, no? As the word says, there will be two coils. Because usually at least there has to be two, right? So one coil this way, another coil this way. So you'll pass current in one of the coils and it will produce a flux which will link the second coil. Phi 2, and that let the current through the first coil. I1. And the flux will be produced by this current, which will link this second coil, Phi 2. So say if there are n turns, n2 turns in this second coil, the total flux will be n2 Phi 2. And this constant of proportionality is a mutual inductance. Okay, so this is the basic concept. So whatever magnetic field is produced by this first coil, whatever field is making this coil, that is the only thing that will contribute to this Phi 2. So the field line which is go like this and go here, that will not contribute to this Phi 2 which is linking this coil. The field lines will going here, that will also not contribute to the flux or Phi 2, I should say, because Phi 2 is the flux only linking this coil. So if I bring these two coils closer to each other, then the number of field lines getting into this or linking this coil will increase, right? Phi 2 will increase, which is the flux linking the second coil, will increase if the distance between the two is decreased. Okay. And also, if I increase the number of turns N2, then also the flux linking this whole coil will increase. So this mutual inductance of this two coils placed like this, and the same two coils will bring closer to each other. So M21 in the second case will be more compared to M21 in the first case. But once I fix the locations of these two coils and the medium which is in between them, then M21 is a constant. But if I'm bringing them closer together, then the mutual inductance will change. Okay, in the first case it will be less because the amount of flux which is linking the second coil will be less. So when M is increased for the same current, the flux linking the second one, same to Phi 2 will increase.
Sir, increase the current means flux will increase.
No, I1 is constant. Okay.
Okay, sir.
I1 is constant. The only thing I'm allowed to vary is the distance between the two coils and the number of turns of the second coil.
Okay, sir.
Okay. So for this given I1, so basically I have to increase the number of flux lines entering this second coil. Okay. So that is possible by bringing it nearer.
Okay, sir.
Okay. But if I use a soft iron core between these two, then the distance does not matter. It's like a transformer then. If you put a soft iron core like this, all this flux which is going on will come inside. So all the flux will be inside now only, in this core only. So now whether I keep them nearby or far away, it does not matter. Okay. But the question is what will happen if this core is not there? So in case of there, I have to bring them close to each other to increase the flux linkage.
Sir,
Yeah.
sir, wave speed for X-ray, visible region
Yeah.
and radio waves.
That is
Can you explain that, sir?
Actually for electromagnetic wave, the speed of the wave is mu to lambda. So if we take light, mu for the light, There is a visible light. Okay, is less compared to frequency of the X-ray. Okay, but the wavelength of the light is more. Wavelength of the light is more compared to wavelength of X-ray. But the product of mu to lambda of light and mu to lambda of X-ray are same. So the frequency is going up, or the frequency is going down, the wavelength will increase such that the product of frequency to wavelength is same for any electromagnetic wave. So X-ray will, what should I say? So X-ray is high frequency, look like this. Visible light will look like this, okay? But the time frequency is time frequency is wavelength. Okay, so velocity is same, right? Velocity is same. So high frequency, velocity is same. Okay. This is the one. So frequency of gamma ray is 10⁻23, but the wavelength is 10⁻40. But for visible light, frequency has dropped to 10⁻40, but the wavelength has increased to 10⁻6. Okay, so the product of frequency and wavelength, which is 10⁻23, 10⁻40, that is how much? 10⁻9, right? Yeah, or 8. Okay, 9 something. Actually, it's 10, and this one 10⁻15 into 10⁻6 is again 9. Okay, so it is the product is same, which is the velocity. So when the frequency is going up, the wavelength will drop down, such that the product of the frequency and the wavelength is constant, which is the speed of the electromagnetic wave. Okay, this accepts as a theoretical concept.
Yes, sir.
Okay.
Yes, sir.
So meter bridge, some people are not feeling comfortable. Meter bridge is exactly same as Wheatstone bridge. Not this one. Wheatstone bridge, go to the derivation of Wheatstone bridge. This derivation you should know. Okay, so one way to remember this formula is R1 by R2 equal to R4 by R3. So I remember like this R2 by R4 equal to R1 by R3. R2 by R4 equal to R1 by R3. So this derivation you should know. Okay, and meter bridge is like this. So this one resistance, this second resistance. These are strips which have zero resistance. Okay, and this wire which is there is split into two parts by the contact point of this galvanometer. So we adjust this point so that current is galvanometer is zero. That is the balance condition. So in that condition, this R by S will be equal to the resistance of this part, the resistance of this part. The resistance of this wire is proportional to the length. The resistance of this part is by resistance of this part be L1 divided by 100 minus L1. So this Wheatstone bridge has got 4 resistors. 1, 2, 3, and 4. There's a galvanometer connecting between these two branches. So this resistance is adjusted such that the current in the galvanometer branch is 0. So for that condition, R2 by R4 is same as R1 by R2. So these four resistors are these four resistors in this meter bridge. One resistance, two resistance, and the third one is this part of the wire, and the fourth one is this part of the wire. So the balance condition will be R by is equal to R1 RCM L1 into RCM is the resistance per unit length of the wire, which is a known quantity. So L1 we can measure. So from that I can get R if S is unknown. Sorry, I can get R if S is known. L1 can be measured from the bridge. So this is the meter bridge. For example, in meter bridge, okay. This is complete. These roots you should know they are very trivial. Just read the book. And the drift current, the mnemonic to remember this formula is this one. So V is the drift velocity, and V just single E is there, and N is the electron number density. So in the case of copper, the number of electron density will be same as number of copper atoms per unit volume, because the assumption is one copper atom will give me one electron. But so number of copper atoms in a unit volume and number of aluminum atoms in a unit volume could be different, because it depends on how closely they are packed. So if number of electrons, number of copper atoms in number of atoms in one metal is more compared to number of atoms in another metal, then the corresponding free electrons will be different. So whichever has got more number of atoms per unit volume have more number of free electrons. So that will have more drift current. So one way to increase the drift current is to choose a metal which has got more number of charge carriers per unit volume, and I can also increase the area of the conductor, cross-section area. So I can increase drift current by these two methods. And also drift velocity depends on the property of the material. So any other question? This thing was there in the previous test itself. And I think one example is in this NCERT book. Okay, so you'll study now on your own. Yeah.
Okay, sir.
Yes, sir.
Okay, sir.
Hmm. Okay, so the meeting will get over in 1 minute. So these are the concepts. Just relax and just study this one. So I think I've almost explained everything. So don't focus on other things. Just focus on these ones only. So with this you can solve. Okay, we'll close now.
Okay, sir.
Okay, good night. All the best.
Thank you, sir.
Good night, sir.
Yeah,
Bye,
I'll be
sir.
there in the exam hall. So
Okay, sir.
fine. Good night.
Good night, sir.
Good night,
Bye, sir.
Bye, sir. Thank you, sir. Bye, sir.
The review is made. Previously, no. Previously. Previously.